The moon turned red. Not in a movie, not in a simulation. On a live NASA broadcast watched by millions of people around the world, the crew of Artemis II looked out the window of the Orion capsule and described something that nobody in mission control had fully prepared them for. Reddish tones, brownish craters, a surface that did not look like the moon. For approximately 4 seconds after that description went out over the comms, nobody responded. 4 seconds. That does not sound significant until you understand exactly who was sitting behind those microphones. These were not first-time observers. These were NASA-selected mission specialists with years of lunar geology training, high-resolution imagery burned into their memory, and thousands of hours of preparation for exactly this moment. And when they finally saw the real moon with their own eyes from closer than any human being has been in over 50 years, their reaction was visible surprise, broadcasted live in front of the entire world. That reaction is the story, not the trajectory, not the press conference talking points, not the technical milestones. The reaction. Because what it tells us is something that nobody in the room that day wanted to say out loud. Every photograph, every orbital image, every rover frame, every training visual we have ever produced of the moon has been showing us something that is not quite real. Not as a conspiracy, not intentionally, but optically, mathematically, instrumentally wrong. And the gap between the moon we thought we knew and the moon the Artemis II crew actually saw is now the most consequential, unresolved problem in NASA's entire surface operations plan. Artemis II launched in 2025. Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen completed a free return trajectory around the moon. No landing, no surface contact, just the closest crewed pass since Apollo 17 departed the lunar surface in December 1972. More than 50 years of distance closed in a single mission. The official purpose was systems validation. NASA needed to confirm that the Orion capsule and the Space Launch System could execute a crewed lunar transit before committing anyone to a landing. That is the version with the orchestral music and the slow-motion launch footage. But inside the capsule, during the approach, something happened that did not make the highlight reel. The crew started describing what they were actually seeing, and it was not what they had prepared for. The detail that stopped people mid-sentence was color. Specifically, the crew described regions of the lunar surface with distinctly reddish and brownish tones, not as a subtle variation, not as a minor shift in hue, as a striking, unmistakable difference from every image in their training library. The surface, in places, looked almost rust-colored, and the faces of people who are professionally selected, in part for their ability not to be surprised, registered something that looked a lot like surprise. Now, here is where this stops being a story about perception and starts being a story about chemistry. Because those reddish tones are not random. They are not a trick of the light. Scientists at the Lunar and Planetary Institute identified the signature almost immediately. What the Artemis II crew was describing is consistent with iron oxide, concentrated in specific crater regions across the lunar surface. Iron oxide. On the moon, which is, in the simplest possible terms, rust. That word matters. Rust. Because rust does not form without oxidization, and oxidization requires a source of oxygen. And the moon, according to the standard model that has been taught in every classroom and cited in every textbook for the last half-century, is an airless, waterless, atmosphere-free rock that should not be capable of producing rust under any conditions we currently understand. The Lunar Reconnaissance Orbiter has been quietly mapping the moon's surface in extraordinary detail since 2009. And buried inside its spectral data, the kind of data that gets processed, cataloged, and filed rather than headlined, are signatures that align precisely with what the Artemis II crew described. Iron-rich regions, high concentrations of oxidized minerals, reddish tones in crater basins, and ancient impact zones that the standard gray tone imagery of decades past never clearly conveyed. The data was there. It has been there for years. The problem is that spectral mapping data and human visual perception are not the same thing. The Lunar Reconnaissance Orbiter was not built with a human retina as the reference point. No lunar instrument ever was. And so the gap between what the instruments were recording and what a human eye would actually see was never treated as a priority research question, until 4 astronauts looked out a window and forced it to become one. Scientists at the Lunar and Planetary Institute are now actively cross-referencing the Artemis II crew observations with that LRO spectral data. The goal is precise: map exactly which regions contain the highest iron oxide concentrations, determine whether those regions align with what the crew described, and figure out what it means for every surface operation NASA is planning to execute in less than 2 years from right now. Because here's the number that should be the headline. The projected cost of Artemis III, the landing mission, is estimated between $4 and $6 billion for a single flight. The space launch system that carries it costs approximately $2.2 billion per launch. Every EVA traverse, every sample collection sequence, every navigation decision on the surface was designed and rehearsed against visual models that were never validated by direct human observation. And those models did not include rust. If the Artemis II crew was seeing iron oxide concentrations that no training image ever conveyed, that changes the entire picture of what the surface looks like under direct low-angle solar illumination. The lunar South Pole, which is where Artemis III is targeting, receives sunlight at angles between 1.5 and 3 degrees above the horizon. Not overhead light, not diffuse studio light, almost horizontal light, grazing across every ridge and crater rim, saturating every mineral surface with side-lit color that no overhead photograph has ever captured. That lighting geometry is exactly the kind of condition that would amplify iron oxide coloration. Low-angle sunlight does not wash color out, it saturates it. It throws shadows that stretch for kilometers and pulls spectral detail out of mineral surfaces in ways that nadir-pointing cameras orbiting 60 miles above the surface simply cannot replicate. What the crew saw may have been the first accurate visual representation of the South Pole region that any human being has ever witnessed. And what they saw was red. So now the question that nobody in the public briefing wanted to ask out loud is sitting there anyway. If the moon has rust on it, where did the oxygen come from? The standard model of lunar formation holds that the moon coalesced from debris ejected when a Mars-sized body called Theia collided with the early Earth approximately 4.5 billion years ago. In that model, the moon formed hot, fast, and airless. It never had an atmosphere. It never had liquid water, and it should not have rust. But some geologists are now seriously considering a different possibility, a possibility that the presence of widespread iron oxide directly supports. There's a growing body of scientific thought suggesting that the early moon may have had a thin, transient atmosphere, not a permanent one, not a breathable one, but a brief geological window, perhaps tens of millions of years, during which volcanic outgassing and residual heat could have produced enough oxygen-bearing compounds to begin oxidizing iron-rich surface minerals. If that hypothesis is correct, it does not just add a footnote to the standard lunar formation model. It rewrites a foundational chapter. The moon billions of years ago was not the dead, airless rock that every textbook diagram shows. It was a geologically active body with a chemical history complex enough to produce surface rust. And we sent 12 people there and brought back 842 pounds of samples, and somehow managed to underprioritize the reddish minerals sitting in those archive boxes for 50 years. The Apollo program returned samples from 6 landing sites. Every gram has been cataloged, stored in nitrogen-purged vaults, and studied by researchers across 5 decades. The collection is one of the most analyzed extraterrestrial datasets in existence, but almost none of that analysis has been conducted in the context of what those samples look like to a human eye under simulated low-angle sunlight that matches the actual lighting conditions of the lunar surface. Controlled laboratory lighting is overhead, diffuse, and constant. The lunar surface is none of those things. NASA is now reportedly running illumination experiments, placing Apollo sample trays under simulated low-angle solar light sources to test whether the reddish and brownish tones the Artemis II crew described are reproducible in a controlled setting. If they are, and if the explanation is mineralogical and tied to iron oxide concentrations, then the primary response is recalibrating training visuals and navigation simulations before Artemis III. That is a solvable problem. Difficult, time-constrained, but solvable. If the experiments cannot reproduce the effect, the implication is considerably more unsettling. It would suggest that what the crew observed was partly a product of the optical environment of cislunar space itself. Full-spectrum unfiltered solar illumination at 239,000 miles, striking a surface with no atmosphere to scatter or soften it, interacting with a human visual cortex in a way that 50 years of camera technology has never been designed to replicate and never needed to until now. Here's a number that should have been reported more widely. This is not the first time astronauts have said the moon looks wrong. Apollo 8, December 1968, Frank Borman, Jim Lovell, and Bill Anders became the first humans to see the moon from close proximity in real time, and their verbal descriptions during the mission were emphatic. The surface looked nothing like the photographs. The shadows were absolute black in a way no image had conveyed. The contrast between sunlit terrain and shadow was more extreme than any training visual had prepared them for. Apollo 11, Neil Armstrong's post-mission technical debrief contains explicit language about the visual surprise of the surface color and how it diverged from training imagery. Buzz Aldrin described this ground beneath his boots in terms that do not match the gray palette of any photograph taken on the same day. Apollo 12, 14, 15, 16, 17. The pattern holds across every mission. Astronauts consistently described a visual reality that did not match the photographic record. Those descriptions exist in the transcripts. They are publicly available, and they were filed away and left unresolved. Not suppressed, not classified. Just noted and set aside because after Apollo 17 lifted off in December 1972, there was no program that needed to act on them, no follow-on crewed mission, no one going back. The data gap was real, but inconvenient, and inconvenient data without a mission to force resolution tends to sit in archive boxes until something drags it back into the light. Artemis II just dragged it back into the light, and this time, the iron oxide data came with it. We have more images of the moon than of any other object in the solar system outside of Earth. Terabytes of spectral data, gravity maps, thermal scans, radar cross-sections, craters mapped down to 1 meter in diameter across the entire near side, and we apparently do not have an accurate representation of what a human being standing on that surface will actually see. 6 missions, 12 moonwalkers, decades of recorded visual discrepancies, and a spectral dataset full of rust that nobody connected to the visual experience until now. That is an extraordinary statement to make in 2026. We are living in an era in which the James Webb Space Telescope identifies molecular signatures of water vapor in the atmospheres of planets orbiting stars 1 out to 100 light years away, in which commercial satellites can resolve individual objects from low Earth orbit, in which artificial intelligence generates photorealistic environments that have never existed. And the single closest astronomical body to Earth, the one that humans visited 6 times, has never been accurately documented in the one dimension that matters most for the people going back. What does it actually look like? Not to a camera, not to a spectrometer, not to a multispectral imager calibrated for scientific interpretation, to a human eye, standing on the surface, under direct solar illumination with no atmosphere between the photons and the retina. That question was never the priority because the assumption was that a camera and a person were equivalent observers. The Artemis II crew walked up to that assumption on live television and broke it, and the rust was sitting there underneath the whole time. The implications do not stop at the moon. When we send humans to Mars, which every major space agency with a crewed program is actively planning, the same gap will be there. The same assumption will be embedded in every training simulation, every surface navigation protocol, every EVA planning tool. Except on Mars, the crew will not be on a flyby. They will be on the surface with 8 to 24 minutes of communication delay in each direction, with no abort option, in an environment no human has ever entered. When the surface looks different from the simulations, there is no one to call in real time. But the moon is where this gets resolved, or does not get resolved. NASA has approximately 12 to 18 months before the Artemis III launch window. That is the full available timeline to study the crew observations, update the training visuals, cross-reference the iron oxide spectral data, and determine whether the rust on the lunar surface changes what astronauts will see, how they will navigate, which samples they should be targeting, and what the chemical history of the surface means for the resource extraction plans that the entire future of deep space exploration is built on. Because here is what iron oxide on the moon actually means beyond the visual. It means there may be a source of oxygen locked into the surface minerals themselves, oxygen that future lunar missions could potentially extract, oxygen that changes the economics of long-duration stays, oxygen that, if the early atmosphere hypothesis holds, tells us that the moon's chemical history is far more complex than any model currently predicts. The rust is not just a color problem. It is a resource problem. It is a formation model problem. It is a question about what the moon actually is. The moon turned red. 4 seconds of silence, and then the most expensive and consequential crewed space program since the original Apollo is sitting in a room somewhere right now pulling 50-year-old sample data and trying to figure out whether the rust they are finding changes the mission, the timeline, the training, or the entire foundational story they have been telling about the closest object in the solar system for longer than most people have been alive. The window is open, the clock is running, and the surface looks different than the picture.